The first type of oscillators that we're going to look at are RC oscillators, or oscillators consisting of resistors and capacitors. The first one of these that we're going to consider is our phase shift oscillator. And so what we can see here is that we have two op amps configured in a buffer configuration. So right here and here we have two buffers. And so the reason we have those is it's going to eliminate our loading effects of these RC filters on one another and make our analysis a little bit easier. But what we see on sort of what we're focusing on though is we have three of these RC filters. And so I'll write explicitly why we can treat this one on the right the same as the other two. But basically we have three RC filters sort of one after the other cascaded. And then finally at our output we have this amplifier. And so what we're going to do is we're going to see if we can't determine what the phase around this loop is. And we know that if our loop gain, if we can make that such that it has a magnitude of 1 and a phase that is 0 or a multiple of 360, then we can have oscillation at our output. So let's label some of these. Let me label these as A1, A2, and A3. And so as we said before, our A1 and A2 are buffers. So A1 and A2 are buffers, and what that does is that's going to eliminate our loading effects and make our analysis a little bit easier. And we're going to come back and compare to what that is without the analysis a little later on, I believe. So we're eliminating our loading effects, and then if we look closely at our configuration with A3, we notice that that's going to be an inverting amplifier. So this is an inverting amplifier. And again, as I mentioned, we have these three RC filters. So taking a closer look at that, noting sort of some other important things, is we notice that our inverting terminal of our A3 amp is at a virtual ground. So right here we have a virtual ground. And so that's if we're assuming these are ideal op amps. Remember, we're saying that the voltage difference between the input terminals is 0. So if our inverting terminal, if our non-inverting terminal is at ground, then it's essentially like our inverting terminal is at ground as well. And so because of that, we have the same configuration for our three RC filters. So same configuration for three RC filters. Okay, so another thing to keep in mind is that because this is an inverting amplifier, it's inherently going to be providing a negative 180 degree phase shift. So inverting amp is going to provide negative 180 degree phase shift. So knowing that, we can then see what we need from each of our three capacitors. So we can then say, well, we want 0 degrees, well, let's be more general. We want n times 360 degrees, where remember n was an integer, so 0, 1, 2, and so on. So what we want sort of in our simplest case is, and this is for our loop gain, T, so this is for our phase. So this is for our phase of T of j omega equals n times 360 degrees. And so what we can see then is if we already have this negative 180 degree phase from our amplifier, if we have a positive 180 degrees from our three RC networks, then we'll have a net 0. So let's say overall feedback network should supply positive 180. And so what that means is because we have three RC filters, if we say each of these RC filters is the same, which again is going to make our analysis easier, that's why I have each of these labeled as C and R, so they're the same variables. So that means if we have 180, each of those three can pick up a third of that. So that means each RC filter will be responsible for a 60-degree phase shift. So each RC filter provides 60-degree phase shift. So again, sort of taking a step back, big picture, we've said ultimately we want our phase angle to be n times 360 for our loop gain in order to have oscillation. And we know that our inverting amp is providing negative 180 degrees to the phase. So we want our overall feedback network, sort of besides the inverting amp, to provide a positive 180, so that we have negative 180 plus positive 180. So we fall into this case here where we have a phase of 0. And because we want positive 180 from our whole feedback network, and we have 3 RC filters, we can then say, well, each of those RC filters should be providing 60 degrees of that phase shift. So a couple other assumptions that we can state really quickly is, we've not talked about this explicitly before, but our operational amplifiers are going to have some frequency effects, and we're assuming that the frequency effects of these op amps occur at a much higher frequency compared to this frequency response. So assuming that the frequency effects of the op amp occur at much higher frequency, and so that's much higher frequency compared to our RC networks. And we've also, again, assumed this input signal VI, but what we're going to see is that we don't actually need that if we're considering this case of a net zero phase, but we've just included it here to aid in our analysis a little bit at the start. Okay, so let's take a closer look at this circuit then. So if we focus on this first RC network over here, what we can see is we essentially have a voltage divider where our V1 is going to be our voltage across the resistor. So we can write that as our V1 is equal to that V input, which again we're kind of arbitrarily saying is there, is equal to our resistance divided by the resistance plus the impedance of the capacitor, 1 over SC. So we can make that form a little simpler if we multiply the numerator and denominator by SC. And so if we do that, we have this is then equal to our Vn times SRC divided by 1 plus SRC. And so we said all 3 of these are identical, so 3 identical RC networks. And we said that with those buffers, we have no loading effects. So what we can do is we can then simplify, and we can say, well, we're just going to have the same thing 3 times. So we could then say our V3 divided by Vn, and so let me come up here. So our V3 we can see is defined right here. So we're saying after we've gone through 1, 2, 3 of these voltage division processes, we're basically just going to be multiplying that same thing 3 times. So this is then going to just be that sort of transfer function that we found before, SRC divided by 1 plus SRC, and because we did that 3 times, we're going to multiply through by 3 times, so we say that's cubed. And so this is actually going to be equal to that feedback transfer function, which we see now explicitly is a function of frequency. So this is our frequency selective feedback transfer function. Not sure what happened there. Let's clean that up. So frequency selective feedback transfer function. Okay, and so to be consistent with the notes, let's call this equation 1. So now let's take a step back and let's consider our gain equation for our inverting amp that we've developed in previous classes. So we want our gain of inverting amp. And so we know that gain A of S is equal to V out divided by V3. So V3 was like our input to that inverting amplifier. And we know that's going to be equal to negative R2 divided by R, where R2 is sort of our feedback resistor, and R was the resistor connected to our inverting terminal. So we can see all of that by looking at this section over here on the right. So if we want to find our overall loop gain then, so to be consistent, let's call this 2. To find our overall loop gain then, what we're going to do is multiply equations 1 and 2 together. So we know our loop gain, T of S, is defined as A of S times our beta of S. So again, plugging in those two equations, we have a negative R2 over R times this SRC divided by 1 plus SRC cubed. Okay, so it's easier to manipulate our calculations when we have this S, but keep in mind this S is equal to j omega, so if we actually want to look at what's going on with our frequency, it's best to put that j omega back in there. So let's go ahead and do that. And I'm going to skip over sort of some of the steps. I'm kind of going to explain it briefly, but if you have further questions, feel free to let me know. So sort of a key thing as we do this is keeping in mind that j squared is equal to -1. So in this numerator here where we have this SRC squared, what we're going to have is we can pull out a j omega squared times RC. And so basically what we'll have is from one of those j squareds, so we'll have something that looks like this. So we'll have a j omega RC that we pull out, and then we'll have a j omega RC squared. And so the j squared is going to become -1, and that's going to cancel out with this negative sign out front. So notice I did not include that down here. And we're going to be left then with just a omega RC squared. So we get something that looks like that. And in the denominator, using those sort of same ideas, we have our 1 plus SRC, so 1 plus j omega RC cubed. Factoring all of that out and keeping track of your j squareds equal to -1, what we get is a real part, which is equal to 1 minus 3 omega squared R squared C squared plus an imaginary part, so j times omega RC times 3 minus omega squared R squared C squared. Again, if you have details on questions about details on the math, let me know, but we're not going to be too concerned about that. So for our oscillation, we had sort of two conditions that we wanted to meet. So for oscillation to begin, we said we have to have the magnitude of that loop gain function is equal to 1. And so let's say this occurs at some frequency omega naught. And remember, as we've already stated, we said that the phase of that loop gain function has to equal n times 360 degrees. And as we talked about earlier, in this case, we can focus on n equals 0. Of course, we can have n equals 1, 2, so on, but in this case we're going to focus on that n equals 0, and that means that we don't have to actually apply any separate input. Okay, so let's sort of look at each of these in turn. So first, let's look at satisfying this angle of t. Well, so let's write it a little differently. Let me come down here and write this whole thing. So we want our t of j omega naught to be equal to 1 angle 0. And so keep in mind, this kind of contradicts what we said in our feedback stability unit because we had 1 angle -180. But of course, again, here we have a -180 degree shift from our inverting amplifier. So that's why that looks a little bit different. So in order to satisfy this, the imaginary part of equation 3, it has to be 0. So the imaginary part of equation 3 must be 0. And so let's look at what equation 3 was. So that was this big mess here. So if we look at equation 3 and we say the imaginary part has to be 0, well, we look at the numerator and we see that the numerator is purely imaginary because we have this j term here. So if we want our overall t to be purely real, then that means our denominator has to be purely imaginary. So we want to just have this term here. So ultimately what we're saying then is we want this term in the denominator to be 0. So basically the takeaway from all of that is that we want 1 minus 3 omega squared times r squared times c squared to be equal to 0 for this condition to be true. So if we solve for that, what we get is that our omega naught is equal to 1 divided by the square root of 3 times RC. And so that's going to be the frequency at which we begin oscillating. And so let's call that equation 4 to be consistent with our notes. So what we can do, of course, is we can plug this equation 4 into our equation 3 up here. So let's say plugging 4 into 3 So plugging 4 into 3, what we then get is we get that our transfer function, or our loop gain function t of j omega is equal to r2 over r1 times j times 1 over root 3 times 1 over root 3. Sorry, that one is just 1 over 3 divided by, now by design this real part has gone to 0, plus j times 1 over root 3 times 3 minus 1/3. So again, by design, what we can see is that these j terms are going to cancel out. So we get these j terms canceling out, so we have a purely real valued number. And what we see is that this is then equal to r2 over r times 1 over 8. So what we now need to consider is this condition that the magnitude of our loop gain is equal to 1. So remember that we want our magnitude at this frequency to be equal to 1. And so what that means is that our R2 over R is equal to 8. But we need to keep in mind that this is the limit that separates sort of our stability and instability. So this is our limit between stability and instability. So if we want spontaneous oscillation, then we want that ratio of R2 to R to be higher. So spontaneous oscillation means we want R2 divided by R to be greater than 8. So another way of saying that is if the gain of our inverting amplitude of our inverting amplifier has to have a magnitude greater than 8 for our oscillation to occur in this circuit. And so we're going to come back in our next video and we're going to look at an example of how we can use this equation to determine oscillation frequency for a given circuit.